The back too. You don't have to ask any of them, but that way, if you want to, if no one's asking, you can pick one. Or ask Derek to do it. Wow.
That's true. I would say
Now I have to pretend it's I have to make it a math. And then that now. Now you can tell. Now it's my good. You good? Okay. So you guys ready to get started? Okay. Ryan, are you ready? Okay. I don't know if you want to sit first, or I'll welcome you and you can sit, but
I'm just going to go sit.
We'll go up there. Project.
Test.
Does it work? Nice.
Yes. Sitting in chairs.
Yeah.
Spread out.
There we go.
Spread out. No one should see you eat it.
Hey guys, we're going to go ahead and get started in a few minutes here. Thank you all so much for coming out tonight. This is a security and IoT panel brought to you by the Women in IoT Meetup and also Neustar. Thank you so much, Neustar, for hosting us. We are all from Neustar on the panel tonight, and we're really excited to talk with you and share some thoughts about the direction the security and IoT space is heading. A few quick things, if you haven't found it already, there's restrooms through that door, past the elevators and down to the right, if you need to use those at any time. And yeah, with that, Neustar is an information service company specializing in marketing and data platforms. We also specialize in IoT. And we are really focused on the different frameworks and security affecting the IoT space as we see it growing. In 2020, there's projected to be billions of devices connected, working in industry, in our homes, our cars, you name it. And one of the biggest things facing us is how to secure those systems. We see cybersecurity moving from personal data attacks to big data attacks and affecting things like taking out whole power plants, shutting down our lights, you name it, and sending in bad data when machines are making a decision can really shut those things down and affect everyone more than just having your Netflix password compromised. This affects, whole cities. So that's what we're thinking about here. And joining me tonight is Ryan Medlin, the director of the engineering team here at Neustar, Josh Treadwell, and Ian Lindsay, both engineers on the IoT team. So welcome. Thank you. Yeah. How you guys doing?
All right.
Great.
Good?
Great.
Cool. So just to get us started, security is a huge space, and there's a lot that goes into that. So we just discuss a little bit what are the different areas of security and what are from anomaly detection to authentication, privacy. What are those? What does that mean, and what does that mean especially in the space of IoT?
You guys are all looking at me. So it's a hard. Security is kind of a hard word. It's kind of a blanket that you have authentication, which is the person I'm speaking to really who they claim to be, versus concealment or privacy issues, which is no one else but the person I'm talking to can see what I'm saying. And those are two independent issues. they're often tied together because sometimes those, one thing is useless without the other, depending on your use case. So going forward, I'll try and specify which of those things is being talked about. And there's the physical access issue, which isn't really new. I mean, desktops have had TPMs optionally for 15 years, as far as I know. So physical access is always an issue, but it's kind of being brought up again afresh. Now that all these things are deployed in public places.
Yeah, and there's also authorization, which is like, it's the next step. It's policy. It's dealing with, you can't do anything without the other prior to. And then there's application layer, then there's transport layer, and there's all these stacked situations where you have to make sure that no one got in one step or they would get the rest of the message. So it's not just making sure you have one set of security measures. It's layering it many, many, many times to a certain degree. Depending if you're talking over 20 hops, there's potentially 20 separate authentication mechanisms happening every single time. And yeah.
And another good way to identify places is to kind of go the opposite way, which is threat modeling. Coming from the hacker perspective, there's a lot of different types of attacks, right? There's spoofing. There's about 5 primary types of attacks: privilege, elevation. So coming at it from a hacker perspective, you're like, okay, how do you get the credentials to spoof to be someone else? How do you elevate your privileges as authorization sort of hack? So coming at it from a hacker perspective, the different types of attacks, you can sort of work backwards from there and be like, what parts of my system am I exposing to those attacks? So
you really have to think creatively about it and to find those vulnerabilities and weaknesses. So it's a lot. What do you think the biggest security risk, what areas do you think are most vulnerable? What's the biggest focus now? Like you said, the desktop's been around for a while, so that's,
Yeah, IoT security isn't really anything, it's not new. And so it's not anything that's really different than standard network security, except for the fact that you're dealing with constrained devices, which can't really do a lot of complicated crypto sometimes. So you're limited in what you can do. The amount of key rotation, if you're dealing with an offline case, you can't revoke privileges necessarily. And so all it really does is makes the issues that we've kind of glanced over for years by, okay, we authenticate with the cloud, we have a known third party, we can pre-share keys easily with deploying binaries. But now if you're ever trying to move key material to a device, it becomes way more of an issue now because there's so many steps in between. You have protocols that you're dealing with protocol translation, and every single time if you're converting from, say, like an IP internet to Bluetooth, there's not a standard way to tunnel key material over that to a device on the other end. And so that middleman, that gateway becomes an attack vector. And so what we're trying to do is build cleaner ways of exchanging key material that way.
Yeah, that makes sense.
Yeah.
It sounds like the where to authenticate and how to standardize that and make it work not just through one device but across the network too becomes really challenging, especially as the space grows and you get bigger verticals merging onto IoT.
And I think one thing, this isn't really cool or technical, but it's the world we live in, and it's the reality we live in, which is the lack of a true business case for security. So what are most of the attacks? Hard-coded credentials that are in a manual, or very basic things where a proper cost associated with a software security lifecycle, spending enough resources up front to do the proper threat modeling to prevent these things. And a lot of times under deadlines, how much is it going to cost to build this? $100,000 if we build in for security. We need to do it for $30K, and we need it to be done in 30 days. Security becomes an afterthought because there's no business case. So what we're seeing now and what we feel like in the next, as we're seeing is major security release are major penetrations because someone attaches an IoT device without a proper security life cycle, attack it, and then that's an event. Once you get it that in, you can use it to attack a lot of different things or to pass information outside. So.
It's always the places that are neglected that are the easiest marks. You know, everybody really secures the nuclear launch codes, but they don't always lock the door. So it's, you know, front door's got lots of security, but that window's unlocked. So there's nothing that's safe. You just have to audit things, make sure that you've covered all the bases that you know about. But you're always going to have losses. You know, people are clever. You know, they figure stuff out quickly. So it's an arms race.
Yeah.
Security in general.
That's a good way to put it. Kind of just for discussion, but what is the aftermath cost, do you think then, in regards to like technical cost to patch a system, and the business cost if your security system is compromised?
Want to talk about any?
I mean, it's just like, this is a thought discussion. I know we don't have exact numbers. And
I mean, it really depends on the use case. I mean, if it's just sensor data, it's as sensitive as that sensor data is. I mean, if you're relying on that sensor data to report something to a critical system that may affect something else, then it's in your control path, and then you're in trouble because that's a potential thing you could alter to trigger something else to happen that you might not necessarily want to happening. And so, I mean, and then as soon as you start saying, okay, a door lock that can be opened remotely, then it's far more. So, I mean, or if it's industrial systems, infinitely more. So,
it really becomes like exponential once your vulnerability is exposed. Yeah, that makes sense. So it sounds like it's really important to consider this from the ground up when designing your IoT system. So that said, let's go into more design questions. How do we do that? Talking about authentication, where do you think it's important to have that authentication level? At the user level or cloud, both, everywhere, nowhere?
Ultimately, the responsibility for authentication, if you care about that, is on the part of the endpoint. So if the device is itself going to care whether the message getting to it was sent by who it thinks it was sent, that's where the auth has to happen. Is because if you don't do it there, that's your attack point. It's like, okay, just however this other system that's talking to this device is convincing it that it's who it thinks it is, it's easier to emulate that than it is to defeat it if it's self-contained in the device. So my position would be from the first place where you have software. So the first place you have the ability to authenticate, and that's in the device, that's where you ought to do it at minimum. The cloud issues are another matter, though. Passing to you.
Yeah, you start dealing with you can think of all these individual devices, if they're interacting with each other versus just a user, as microservices to a certain degree. There's a lot of analogies of dealing with machine-to-machine communication as just kind of APIs. And so you want to make sure that the client wants to trust the fact that it's talking to a server, and then the server needs to trust the fact that it's talking to the correct client. And then there's, with every exchange in there, there's a possible man in the middle. There's a possible aggregation. And so you have to worry about, okay, if I spoke to the server last time, I have to make sure that the next time I talk to it, it's actually the same one again. So how do you time out things, like how your nonce is working and rotating keys? And there's a lot to worry about, especially if you're trying to go, again, like we've been dealing with this for the offline cases, that if you're distributing key material to be used later, how do you properly time that out and deal with, okay, if the power cuts, we need to make sure our machines keep working, but how long? Or, if someone does cut the power in order to attack me, what's the timeline on that? How am I able to revoke it? And so there's, authentication is a complicated thing, and it's just verifying who you're talking to. And then that comes into policy as well. So, it's what can this person do that I'm talking to? Yeah.
Yeah, and how to get the new keys or refresh those if it times out. That makes sense. This seems like a lot of this, as you are testing your system, this would come up. like we said before, it's weaknesses in the system that will eventually like cause the whole thing to come crashing down. So how do you think about testing and security, and how to, you have your main path, but you have to check all the vulnerabilities too. So is there any typically we do like API tests, but we also just have to like bang on it too. Is there any like unique design challenges when testing security in IoT?
I guess it would depend on what your responsibilities are. It's like, sorry.
Yeah, go ahead.
It was like I have a host of things that I check for writing firmware, but that won't apply to everybody. So you could spend all of your time error checking something and never find anything, and it's a trade-off. Peer review, I would say, is the most reliable way to go.
Right, and so that's where the design, that's where the cost comes in. We're developing a secure system, right? You literally need to document every touch point of the architecture, what the potential threats could be at those various touch points, in great detail, and then a tester could either automate that or, I'm pointing at a tester over there. They can use those documents to go through it, and then again, your test cycle upon every change needs to be automated, and you got to build those tests. So actually modeling it out, documenting it, and then doing the automated test on every change, every iteration of a release. That's where the cost blows up, but we feel it's going to be very important because the downside of the breaches and then making changes after the breaches are probably 100x the cost of doing the design up front.
Yeah, that makes sense. We always say in software, testing as you're developing is crucial, but especially in an IoT system, it seems extra critical since there's a lot of communication and machine-to-machine decision-making happening.
Yeah, and it's again, like with all security, it's always important to plan for what happens afterwards, after you're already breached versus preventing yourself from being breached. And so you want strategies on, post-breach revocation and making sure you don't have a wildfire spread immediately if one breach happens. And so it's properly scoping out, what's possible with one set of keys, essentially. So.
Yeah, are there, I guess, different checkpoints you can set up in design? So like in the case with Ukraine at the beginning of the year when they were compromised, their power grids went off, their power plants were hacked, and the hackers basically got in, and once they were in, they were able to take control of all the operators' computers, and it was really hard for them to override because they had access to everything. So is there some checkpoints you can to kind of silo off different areas so you don't have access to the whole system? And I guess preventing kind of those backdoor entry points for potential threats.
You could take those kinds of strategies, but you risk introducing another DDoS opportunity. No 1D there, just denial of service. So if you put in a big red button, kind of a kill switch, I'll attack that. So it's really the best advice I've heard regarding this sort of thing is you want to increase the cost of an attack, whatever cost might mean to you at that point, and lower the return that you would get from a successful breach of your security measures. Right. So you're going to get hacked eventually. Everyone does. But if there's no return from doing it, there's usually no reason to engage in the attack.
And some of the research we've done in anomaly detection is we try to at least, how to capture enough data exhaust and have a real-time sort of pipeline. The vision is to have some sort of anomaly detection to detect it early, and then based on those detections to have sort of almost real-time sort of, if you see X, Y, and Z sort of alerts or notifications get thrown, then perform X, Y, and Z to your IoT infrastructure. And enabling that, you need standards and everything in order to consistently sort of roll out some sort of security defense mechanism, so it's detected early via real-time pipeline, and then immediately be able to roll out a sophisticated change in your IoT network topology or devices to sort of put a wall around it. But the technology's not there yet. We kind of feel like we're working on R&D around that, and what does that look like? And standards sort of make that a little bit more possible. Once you have standards, you can kind of have everyone can kind of conform and focus on the data, and then what are the type of responses instead of building a different response for every platform, for every device. That's where the cost just kind of blows up. You can't try to attack those problems.
Many of our internal discussions regarding PKI strategies have revolved around exactly that issue. Is okay, how do you cope with somebody getting into one thing or another? So revoke access to that thing. But if that thing's not connected to the internet, how do you deal with it? So have you ever tried to flash the firmware on your doorknob? How do you do that? It's like once this stuff gets released, it's done. It's there's always going to be at least one of those things that's out there with some guy has a doorknob that doesn't work and he doesn't know it. So those are very difficult issues. There's not going to be one solution to them.
Yeah, that is really important, and kind of digging in more to standards. So we have standards at the device level, but also gateway and cloud. Why is it so important, and what are the important standardizations to consider at each of those levels?
Having a standard is important because there's an objective place you can point to look implementation versus standard. The standard says this, the implementation is doing this, the implementation is wrong. Mm-hmm. So it's kind of an intellectual touchstone for people who have built implementations who's at fault when this doesn't work? So that's the value I get out of it.
It's also ecosystems. Right now, generally, there aren't really many standards. I mean, there's a few methods out there, I guess, for constrained devices to discuss things, but it's not. There's no application layer, kind of semantic way for these devices that's all universally agreed upon. That I can't just tell my light to turn on or the door to unlock. I have to program something specifically or build a bridge between every possible application protocol. So I mean, we have a few messaging protocols that are up and coming and work well enough, but there isn't a general way to deal with them short of very specific translators between every single protocol. And so there's attempts to be made. There's OCF and AllJoin and plenty of others. I don't know, way too many. Yeah. And they're starting to kind of work together, but they're we've dealt with the perils of that a little bit. CoAP is up and coming, and it's big with the IETF, so we're kind of moving in that direction a bit too. So, yeah.
And then one thing back to the translation, if you don't have standards, where are you going to translate?
Yeah. That
means you need to add something to your architecture in order to translate. And as soon as you add something, you expand your attack surface. What are you going to do? That's a really prime location to try to attack.
Yeah, so there's like a trade-off between doing that and just having a standard. So there's a lot of attempts to kind of standardize this now, but whose responsibility, I guess, is it to standardize, and how do we collectively as an industry move towards that path?
Well, and standards allow you to abstract interface, essentially, and features and services from hardware to a certain degree, at least in this space. So right now you have hardware developers building all of their own software, all of their own hardware, and all of their own kind of cloud infrastructures. And it's great if you happen to be in all three of those industries already, but it's not great for the consumers, and it's not great for everyone else designing things that I can only work on software, so I can't, I'm not going to release any hardware. It's hard to compete, and it doesn't really lead to the best solution. And so standards really kind of open up the door for hardware people to do what hardware people do best, and then just write against a standard. The software people can come in and offer their solution, and the cloud providers can do what they do best with data processing without having to invent low-level firmware that they have to distribute to get people onto their platform. And so it's all about trying to open up the doors for better services rather than just these closed-off verticals. But oh yeah,
pretty well covered it.
That makes sense. I guess thinking about open source and how that plays into this. Yeah, we like that. So, yeah, I mean, that's one way in software, like we've traditionally kind of solved these problems, is just a community of developers working towards something. Given that, like what are the trade-offs, I guess, and like how does that work when these all need to be secure, but you want to develop an open source standard, and what's your experience working in open source standardization tools?
Man, how long have I been an open source advocate, Josh? Yeah, as long as I've known you at least. So it's been refreshing to see the open source stuff get as much traction as it has, because if peer review is a virtue, then closed source is kind of an anti-value. If you have no way to investigate why something is breaking, you have no hope of fixing it, other than to wall it off and then wrap it in something that is standards compliant. But it's useful to be able to repurpose others' work, but that's only part of the benefit. Most of the benefit is that of understanding, because you can't conform to something you don't understand. And so if there's not an open standard of some sort, then you're just kind of out there on your own, and what you have to take on all of the burden of the consequences of your design changes all on yourself. So it's the fewer uncharted roads you have to go down, the better. The safer it is.
Yeah, and it's like, do you want 5,000 people who love security and are more than welcome to review your code for free? Or do you want a closed system where the people that pay you don't get to see it either, and just you see it and your 5 security engineers see it? What makes you feel more comfortable? You know, I think Ian refuses to. He refuses to put any non-open source stuff on his firmware. He's like, I'm not putting that on my device.
It's not worth the space in my brain. It just can't. Doesn't integrate.
Yeah, that's fair. That's some great points. Ryan, how does open source fit into like a business model for a company? Why is it beneficial for a private company to use open source software, and why would they choose that instead of like building their own vertical like these guys say is happening now?
That's a good question.
Yeah.
It's a good question. And if I can answer, it's a good question. And if I answer it, you can just tell your executives, and hopefully they'll believe it. So we try. I mean, for open source, it's really good to like from the edge, the things that developers care about, like the stuff I'm putting on devices, the things that are making me connect to other things, the core servers serving up content. Those are great opportunities for open source because developers everyone can peer review it in the world, whoever's doing it. You know, you can build these systems, you can get them to work, great. But now what are the value added systems, from the data exhaust or from additional sort of support? These value added services that, it's almost like the people who are reviewing your code aren't going to want to provide you 24/7 support and be on a pager. Mm-hmm. So there's these levels of services that, that you do want to pay money because people who are looking at the open source code, it just doesn't fit. So adding those value-added services, data exhaust, these sort of data analytics algorithms, companies can be really focused on looking at a particular type of data and providing analytics and alerting and some workflow around that. So there is a model there. Some people like the commercial open source model. Some people, they build on top of adding value-added data services and analytics on top of it. So.
Yeah, so it just becomes like part of the scaffold that you can build on top of and is still supported openly, so people can trust that as well. Makes sense. Do you have something to add?
Ryan summed it up nicely. They're not mutually exclusive choices. Apart from licensing issues and that sort of thing. If that's not a blocker, then there's no reason you can't have those two systems, something closed and something open, coexisting in your stack. It's been done before, but it's like the security issues. There's no hard and fast way to monetize anything, let alone something like software. So it costs nothing to copy it. It costs something to write it and maintain it. Distributing it, copying it, it's not really, so the economics of it aren't really directly analogous to things that are physical. This causes a little bit of grief in the IoT hardware market because these guys, Hue, Philips, they make money selling light bulbs, not software. So we end up with this situation where they have this closed software stack that isn't really very good, and they have no direct incentive to improve it unless they can lock you into it. So these are the kinds of situations that we're probably going to be dealing with off and on in some capacity for at least 5 to 10 years. I don't know how long it'll take to sort it all out, but if you find a good way to monetize open source, let me know.
I will do that. Yeah, I guess, so considering open source and standardization, how does that play into privacy? It seems like there could be some issues there. Obviously, we want the source to be open and like have that code available to create a strong developer community. But then you do want your devices, once you're developing and those devices are using that code in their firmware, to have a certain level of privacy.
I mean, it's different to have if you're going to commit your private keys to GitHub, like obviously kind of an idiot. So, but really the source code itself, there's nothing. It benefits from being viewed just because you can spot problems ahead of time to a certain degree. I don't know if there's. I've never really seen the merit in locking code and not showing anybody to protect its own security. If you're trying to actually protect its security, it should be mathematically secure, not obfuscated. Just waiting for somebody to unlock the box in the proper way. I mean, you can scrape the messaging all you want, and then you're eventually going to find some way in, unless it's not feasible.
Yeah.
Actually mathematically through the code. So I mean, yeah, I don't know if there's privacy that you have to worry about in source code really. I think that's largely a cop out. So I don't know. Yeah.
I mean, you can definitely look into open source with a privacy lens, kind of like the security threat modeling and all that, right? You say, we're going to evaluate all the privacy touch points of the open source code base. What is it doing with personally identifiable information, right? Or your system in general? Where are the privacy touch points? How are we dealing with that? And then having a story around that. So.
Yeah, that makes sense. You mentioned earlier talking about the edge. And can you just generally give an overview of the edge and how that fits between the devices and the cloud?
Okay. Yeah. So, yeah, I guess the edge in general just means it means many things to different people. It could mean a data center that's outside of some specific cloud. It could also mean on premises. On the machines you're using locally. The real reason for this is offline functionality. It doesn't make sense to flip a switch and have that message go all the way to the cloud and then all the way back, unless you're the most worried about, some form of specific security. I mean, in terms of bandwidth and just efficiency or wire efficiency, it makes way more sense to have the light authenticate against your switch. And so that, like, you do at the most basic level, you can do kind of like a peer-to-peer authentication. If you're going to do an edge authentication, you have a local device that's doing all of your authentication. And then if you choose to, you can also have a cloud service do that. I mean, that's kind of the remote connection scenario. But I think it's a big deal, especially in terms of enterprise or anybody that's controlling things. So from just a sensor data aggregation perspective, edge is not the biggest thing unless it's really mission critical. You're trying to collect, the internet went out for 10 minutes and I need to collect data for that 10 minutes. That's one use of the edge, is you can cache it offline until you get a connection again. Otherwise, if you want local control, the edge can help you do that as well. And so really it becomes not about, we've used this, and it's trying to make a network of things rather than purely just an internet of things. So and really that comes down to, that complicates things though, because now your authentication mechanisms aren't just in the cloud.
Right.
They're now distributed out to different devices locally, and that's a whole new set of security problems.
Yeah, I wanted to dive into that more. So thank you for explaining at a higher level before we go into that. So yeah, there are a lot of security issues facing at the edge, and I guess just to start, data collection when you're offline and the vulnerability that's exposed there. Let's go ahead and talk about that more. What potential risks are?
Yeah, I mean, you're revoking. Really, it's revocation. So like, I can push out to my edge some possible network configuration that, okay, I want X to have Y access to Z. So I want, my doorbell to turn my light on, but only between, before 10 p.m. and then it doesn't work anymore. Now that's not really a mission critical security situation, but if I ever decided to change that, I can't easily do that unless I'm at home or say the door, the lock opens during business hours. But how do I, one day I'm open on Saturdays, there's a holiday and I need to lock the door. I need to make sure I'm offline or I'm online in order to update the policy. I can't remotely revoke policy from without connection. And that's really the problem that comes into it is how do I maintain my my state out in the world where my actual servers are operating versus what I think it should be in a database in the cloud. Mm-hmm. And so it's just a little bit different because the only thing that matters is really the state on the device if it's doing authentication. So technically, yeah, if you only want, if you require the internet to work, you don't need any offline, and then you can always just make sure you have 0-second revocation abilities. But if you ever want to open your door when the internet's down, you need something like that. So it's like a balancing act.
Yeah, makes sense. Are there any balancing act between that and then all those devices often do like peer-to-peer communication, like you said too. How do you keep those communications secure in both offline and online states?
There's a variety of strategies for that. If you're worried about somebody tapping your wire, you're probably more interested in the privacy, i.e. the encryption, than you are the authentication. So if you're dealing with encryption and you don't know who might be sitting between you and your counterparty, you probably want to also do authentication. You want to make sure that it's like, all right, I see this is encrypted, but if somebody else sent it to me, it's no good. So this goes back to that split between those two separate issues that nevertheless are tied together very, very frequently. TLS, which is the successor to SSL, which I don't know if most of the people in the audience are programmers or not, but I figure you've seen the lock in your browser. So there's a variant of that protocol that we're using for CoAP anyhow. And MQTT also runs over TLS. So those same strategies are applicable pretty much everywhere where you have IP. The only difference is in the space in which you have to actually make it happen. So it's not a whole lot different than the security on the rest of the internet in that regard.
Do you have anything to add?
Do you want me to expound on?
No, not really. I mean, the only thing is, yeah, I mean, in like the standards like OCF, they do policy enforcement on the device, right? So just, it's doing all of that, and it could have a sophisticated policy on the device, and it's doing it. So that's kind of that characteristic is very interesting, and not a lot of IoT platforms out there really do that. The OCF standard does, and that's kind of the distributed nature. How do you have a peer-to-peer, but also how do you be able to manage that from the cloud as well to push these policies down? And once the policy's there, the policy's there. The device is the authoritative enforcer of it, right?
Yeah.
The browser comes shipped with all of that auth information by default, but we don't have that luxury all the time. So that's a little different as well.
Yeah, that's the scariest step in any of this is this provisioning. And so anytime the browser comes pre-shipped with the public keys of all of the certificates.
CAs.
Yeah, you have CAs that you trust as when you download your browser that how to trust them. The hardest part is getting the initial key material down to the device that then it can identify its most trusted authority. So I mean, if we can establish standard certificates on devices, but oftentimes they're expensive, and so we're dealing with much smaller devices. You can't deal with it as much. So the amount of key material you can store on a single device potentially is not very large.
I'd like to note that's not necessarily a bad thing too. That we can't get a whole bunch of CAs on a device. In a weird way, that's a blessing in disguise, because the way that privacy and SSL and certificates are handled on the broader internet is broken. It's really badly broken because all the CAs are equal. If you have one CA, your browser, say, ships with 10 CAs. One of them gets compromised. It doesn't matter how secure the other 9 are, because now if you can forge a cert from that one CA, your browser will trust it. So there are a lot of these security issues that we're trying to not repeat the mistakes of the past. But in order to do that, it requires a lot of careful thought. So,
and for IoT, introducing like straight PKI management, to revoke a certificate, you need a sort of a certificate revocation database or whatever, a CRL or whatever. For IoT, that introduces a lot of scalability and architectural problems, because one cannot handle all of your devices at a large installation. You can't just have one. You have to think about sharding that revocation list across facilities or whatnot. So it adds more things to your architecture, more things to manage, another attack surface, and another scalability problem, which all the devices, if we're going to have, what does it say? We're going to have like 80 devices in our homes in the next 2 years, 80 IoT devices attached to our slow routers that can't handle them in the next 2 years.
I'm picturing just like a robot with light bulbs and like Kindles and everything, just making its way through your house. Its feet are Roombas. But yeah, there is a lot of like interesting design considerations. I know at Neustar we're kind of early in how we're thinking about that, but do you have any insights or questions that you're really thinking about now that are kind of curiosities within that problem?
There's cloud salute. There's ways of verifying that in sort of a centralized location that could also be decentralized, where you could say, is this valid? And you kind of do another sort of a check, and sometimes that's in the cloud, but there's a way to sort of move that logic down to like an edge server or something like that. So there's a way to scale that problem. I mean, we know a couple companies that are working
plenty
on
of
it.
like blockchain style distributed hash table kind of central repositories that are decentralized. Really, I mean, it depends on the scope of trust. It's like, why do you trust somebody? Who do you trust? You can generally trust trusted authorities, technically, but I mean, do you want to? You know what I mean? Like, it's a hard question, I guess. It's not really, there's not an easy way to deal with it. There's chained systems, and so that's really what we're kind of looking at a little bit now, is chaining your own PKI structures similar to certificates and things like that. So
basically having a centralized but maybe architecturally decentralized key store, right?
Yeah.
So where all the keys are located in a central location. They could also be, in the cloud, but also live in the edge, and scaling it that way.
And if they were stored in the edge, then if it was offline, it could still authenticate. Yeah. That makes sense.
Well, it's kind of like how like Bitcoin escrow systems work a little bit, is you can have multiple signatures and require at least X amount of signatures in order to authorize something. So it's
somewhat of a departure from the way traditional web PKI works. It's like my exposure to PKIs, from figuring out how it works on the internet and in my browser, is basically, well, Callie trusts you. I don't know who you are, but I trust Callie, and therefore I will trust you. And that kind of thing it works some places. It's really great because it's simple, but it's not always appropriate for situations where you don't have a central point of trust, or maybe someone doesn't trust that, or maybe the networks are more heterogeneous here. It's definitely a hard problem to solve, but been exposed to a lot of new ideas in this regard over the past 6 months or so.
Do you think the heterogeneity will change as standards emerge in the industry, or will that continue to be a problem?
I don't know. there will be bad ideas that die off, and there will be ideas we don't have today that will happen and probably kill off a lot of ideas that do exist today. So there's going to be a lot of flux and turmoil, but cryptography is kind of interesting because there's a lot of really indirect ways to use it, and it's blockchains were one of those examples where there's this really indirect usage of cryptography, and look what it enables us to do, and now I don't think about crypto the same way anymore. So I expect that kind of thing will just continue until I retire. So,
That seems to be how it goes.
I enjoy working in this space, though. So ask me the question again another 3 years, and maybe I'll have a sensible answer.
Yeah. Well, with that, I want to open it up to questions from you guys. Is there anything that you guys would like to ask our panelists this evening?
Depends on what.
I mean, I don't know if there will ever be a central standard for it. Everyone's always going to have separate standards, and ones will have slight advantages over others. Again, there are already standards, but you can buy into a standard to a certain degree, but it's not always going to be the best product. And so, really, I think there will be probably 2 or 3 total in the end, but they should at least be interoperable enough to where you can use what you want. And that's, I would give it a year to 2 years before most of the mess is cleaned up. And until you can buy products that fit inside of that realm. But yeah, following the standards is a frustrating endeavor.
It's work, man.
Yeah,
it's a lot of discipline. You have to
sit there and
do that.
Read things all day, and it's not. Yeah.
Somebody gave an example of the Wi-Fi, sort of the way Wi-Fi, it took years and years and years and years and years in order to get adopted. Then eventually, there it is.
How long did you have a Wi-Fi in router before in became standard? That's one of those cases. Is that what you're talking about?
Yeah, the initial, the initial Wi-Fi standard, it took forever to get adoption, and then after many years, I don't know how many years that people said it was, 7 to 10 years or something.
Yeah.
There's even that case too, whereas even though we have what I don't know if you'd call it a current Wi-Fi standard, people are using standards all across that time period, and sometimes it's for reasons that, the new standard breaks my use case. So we're going to deal with a mix of standards always.
Yeah, it also depends on which standards layer you're talking about, I guess, because that's a whole other nightmare of standard stacking on standards. So there's the 802.15.4, which is like the long-range radio network, or I don't know, low-power, slightly longer-range radio networks. So Zigbee and Z-Wave and Thread are running over those. Thread is looking to be the cleanest one, only because it uses what's called 6LoWPAN, which is an IP network on top of it. And so it allows other things to easily be routed because everything else can ride on an IP address and not have to deal with specific radio routing and things like that. There's a lot. Bluetooth is another one that's separate, but coming along. There's a new Bluetooth spec that's probably next year or something.
Bluetooth itself is actually it's a constellation of standards.
Yeah. And so there's depending on which layer you're talking about. If we're talking wireless standards, if we're talking application standards, if we're talking transport standards, protocol. There's all these different methods. It's never really gonna clean out as long we'll get 80% of the way there, I think. Yeah, and then, security standards. Again, security is already there, and it's coming. None of the security is really all that bad. It's just the fact that we need to implement the security we have on these smaller things.
Yeah.
And so that's really the goal.
So much inventing new standards, but making the ones that exist and have been battle hardened, making them more widely applicable.
Yeah, and it comes back to the interoperable standards only because every time you have to convert data, to a separate standard or separate packet format, you need a little bit of routing information in order to push it to the next protocol, and that becomes an attack surface. And so because the device in the middle has to have enough information to convert that data to somewhere else, that device now isn't just a dumb pass-through that can handle just routing things. It now has to translate and read and parse data, and then you can possibly attack that. So
it's going to take a little bit of time.
Yeah.
Any other questions?
I have a question and a little comment. You mentioned Ukraine, and I'm actually from Ukraine.
Yeah.
And I was involved in CERT-TA looking into that incident. And it's very different from what you guys are talking here about, because there took place complete disregard for security and just lack of confidence on how government and people who set it up. So it's surprising to me that it didn't get hacked like 10 years ago. But anyway, so the question is, the technical constraints, the computational constraints we have in IoT, what exactly do they, like, what cannot be done in terms of the TOS stack to protect communications? Because I remember you said that there are some limitations. Then you said, I'm sorry, this is the beginning. I didn't know your name.
No, it's fine.
Ian.
Josh.
This is Ryan. I'm Callie.
Yeah.
Reauthenticate.
So what cannot be done? What has been done?
I mean, it depends on your scope of IoT to a certain degree, because technically, computer to computer is machine to machine. So, like, we're doing security as it is. So, I mean, in constrained devices in general, you have memory and you have compute and you have, if you're battery limited, you have radio bandwidth. And so there's all, or, wire bandwidth, I guess.
Yeah.
And so in all these scenarios, if you're CPU limited, you can't authenticate or you can't decrypt or do enough work to parse anything fast enough. And thus, in that case, your memory starts filling up because you're slower, and then you can only handle so many messages per second. And so that's like the advent of ECC, which is, as opposed to
ECC is quicker.
Yeah, it's like faster ways of dealing with things. It's a little bit less a little bit less hard on your CPU for the key size. So there's RSA key sizes that you need a substantially longer key that you would need to store in memory and to parse. What's that?
I have a 96 megahertz microcontroller that I use, the TNC3 at home, and I think an ECC signing operation takes about a quarter of a second. So it's a really easy thing to make unavailable if somebody's just throwing garbage traffic at it, knowing that it's going to flood my compute pipeline with all sorts of irrelevant signing operations. In the best case, they simply stop it from working. In the worst case, they actually are able to listen to the power supply and figure out pieces of the key, and then they are able to spoof the device from that point on.
Yeah, it also has other advantages because your key material is small, or the encryption format is smaller. You don't have to store nearly as large of keys. Thus, your memory load is lower. The wire, the amount of data in the packet is less. There's just different things you can do.
If you want to talk nitty gritty of cipher suites and whatnot, I'll be happy to do that with you after that. Okay.
Yeah.
Yeah, just catch me over there after.
And then one other thing is sort of tampering.
Yeah.
I have physical access to the device, so a small device can't have a TPM module or anything like that. So,
they're starting to.
Yeah, starting to, but it's again, as you get smaller, you can't have certain tamper prevention things like a TPM module or something.
But don't you think there should be kind of some kind of standard that is actually enforced by probably, I don't know, the government or upon the companies, so that they actually do make things at least secure in some baseline level?
NIST.
Buildings, it could be just cheaper to build them of cardboard, but we don't do that because we want them to stand and just not fall on people. So there are standards. Probably the same should be done here, because I understand it's cheaper. It's cheaper to have your remote control, just sending the IR signal, and that's it.
I see your point. That's a double-edged sword, though, because if on the one hand we do have that, and in the United States that's NIST that puts out the FIPS the FIPS 140 specification that basically standardizes AES as being, so AES, SHA-256, all of these cipher suites all of this comes from NIST as far as what the recommendations for it go. But then again, a lot of these security breaches, especially those that happen at like state level major infrastructure, government is the perpetrator. So it's not any good to have your perpetrators specifying what you should be using for your crypto. So there's that too. If somebody tells you you must use 128-bit AES and no less, it's like, well, I could use 256, but they say my minimum is 128. I'm doing that. So having a standard declared from the top down is not a good answer. I don't think it's inviting other kinds of problems.
Any other questions? Sorry.
All right, guys. So you have commercials today. All right, now let's actually go to the consumer today. What do you see is the largest vulnerability that is exposed by devices that are likely to be right now?
What's largest?
So
most deployed?
Likely to be hacked or something that most a door has been opened, someone's gained access. I guess what is the most likely? How about let's start with that. What's the most likely hack?
So the most common hack are baby monitors.
Okay, yeah.
You can go, God, what's the website? There are websites that just document every open webcam you can possibly see, and you can just watch whatever you want on random baby video monitors.
Megan threw away our baby monitor, actually.
Yeah, and it's creepy. So, it depends on what's IP connected.
Yeah.
And so, like, there's a lot of IoT devices that are just locally open. So if it's just a Bluetooth device, great. I have to be physically present to do anything to this. Or I plug in a serial port and, or USB port and program it. It's technically a little bit more safe, even if it's unsecure, because it's not globally available.
I would have voted Wi-Fi routers. It's like I've not seen a UPnP implementation in a router that requires a username and password to open UDP ports. No. I won't
UPnP's got some holes. I mean, it's been secured enough that it's hard to get behind NAT unless you're running a server and that device has requested UPnP.
Yeah.
So,
you can always find out what's going on. Yeah, but
yeah. Other than that, I don't know, really. I mean, it's software. It's just bad software that runs a server. Anything that runs a server is potentially trying to open a port somewhere, and you're in trouble. But
in the industrial space, isn't it like any device shipped from China, especially like web closed circuit television cameras? Yeah. Closed circuit shipped from firmware shipped from China. That seems to be a really big wide open door.
The potential, yeah.
All the Tesla hacks. There's a lot of lists of Tesla, Jeep. There's a nice article probably once a month about a car.
Jeep got in a lot of trouble. Was it a year or two ago from that, where they connected their sort of OnStar-like service directly to their CAN bus, which is an entirely unencrypted standard, and you get full access to everything in the car if you can tap into the CAN bus, and so they hooked it directly up to a cell phone link that you could easily spoof with no encryption whatsoever. So if you could in any way emulate a cell phone tower, a GSM cell phone tower, you control any Jeep within your radio's range. It's just people. It comes from a lot of old industrial systems where you're just dealing with networks that don't have any form of security because it wasn't required. Everything was closed. And so they have these big systems they set up, and then they hook one thing up to the internet, and then there's one exploit, and you get access to the entire facility.
I can see that happening. They go, oh, we need to build a Jeep for $1 billion, and we need it done in 6 months. And there's a guy going, yeah, we need to go through a security review and full security audit and threat profile of everything, and it'll cost $200 million and add another 3 months to the project. And then the manager over here goes, what? just kind of puts them over here, locks them in a room, lets them come out 6 months later when the Jeep's out.
To do, take this hard-coded key out of this code. Yeah.
It seems like there's been a major theme here tonight, which is the trade-off between security and performance. That the more you layer on security, you're already talking about issues with performance. And I guess my question is there some point that you wish you could secure more efficiently, but right now, if you do that, it's going to wreck the performance of the platform?
That's a good question. Yeah, that's a serious issue with constrained devices. If it's a hard NP kind of sometimes the lack of performance is the goal. It's harder to brute force a password if it takes 500 milliseconds to test it. The user entering it doesn't care about that half second, but the machine will care if you're going to try it a million times. So, yeah. There's
DDoS spec, an anti-DDoS spec that you require if you hit a server, it will return you immediately a problem to solve. And so you have to algorithmically solve a hard problem and then send back your response before you're allowed to do anything to it. I mean, so there's reasons for that kind of thing, but it's never. I mean, it's like reading a book, and so now imagine scrambling every word in that book 20 times. I mean, it's always going to be more work to encrypt something or to hide something. At least something that you want to send over the air that risks being seen. So
no matter what it is, there's always a non-zero overhead.
Exactly. There's HSMs and things like that like sort of get around this issue, which are hardware security modules that effectively do all that step for you. And so it takes the burden off the microcontroller to do the crypto. So it's sort of a good thing to do, but you're always going to incur the size and everything else. So
there's certain cases where you do want to get things done as quickly as possible, and that's usually in asymmetric signing operations is a common one. It's like I wish it didn't take a quarter second to sign a transaction on my TNC3. I don't really have any benefit to having that go slower. And AES is like symmetric operations are really common where there's no benefit to slowing it down. You want it to move as quickly as possible because it stalls your pipeline. Otherwise. But that's just the general theme in engineering as a whole. It's like there's no one right way to do something. It's always a trade-off, and what choice you make always depends on your values. So that's kind of the situation with the security. Always, no silver bullets.
I think we have time for a couple more if there's anything else.
So in the enterprise world, the standard itself, usually a few big companies get together and they collaborate to find a solution that they enterprise organization which kind of kind of see, and there's doing an extensive computation security that actually address issues like performance devices.
Yeah.
Do you think there's going to be two companies that take the lead, or is it going to be the smaller companies, you guys in the product that are working on something that are actually
I don't know. The TLS puzzles that you were just describing from the last question, they're kind of that. Who pushed those? Do you happen to remember? Was that?
I don't remember who submitted it, but it's an IETF draft.
Yeah.
Or RFC.
IETF, you don't really have companies affiliated with standards in that case. But yeah, I see your point though. Is usually in order to get the standard out there and actually get it used, there's some interest behind it of pushing it out there. It's like the way I've seen that evolve organically, though, that I really like is when it's just quick. Quick's an example of that. It's meant to address some deficiency in the TCP. You go to a website and there's 6 transactions before you get your web page back. It doesn't need to be 6. It might be 3. And so there are these kinds of but. The adoption is gradual, and generally it's one company or one individual sometimes that pushes that standard and drafts the spec, and it sits there for 20 years. There's stuff out there that's been sitting on the shelf for decades. Some of it will never be used. So it's kind of fun to go through the IETF spec list occasionally, just choose random RFCs. They have sub lists for humorous RFCs, most active, least active, that kind of thing. And sometimes you just browse through there. It's like, man, what kind of kooky ideas did people have? And so yeah, the vehicle for getting things standardized like that is I think the minimum condition is that two people need to talk to one another. And as long as that condition is there, there's the potential for a standard to spread.
Yeah, and closed standards in general aren't really standards necessarily. Yeah. They might be like an internal company standard, but they don't really go too far. I mean, even I'm thinking of closed standards. There's like PDF, for example, is still an open standard to a certain degree because they were forced to because other people were competing with it.
Reverse engineer PDF, or was that? Did it release PDF? Or
they released a subset of PDF that you can. Yeah. Anyway.
Okay.
Yeah. So.
Knew that. Yeah.
So really, it's standards are more about communicating with other companies. It's not generally a company that comes up with it. It's an agreement. Even if one company invented it, it's an agreement with other people to interop with it. So I don't know if there's necessarily going to be one company that comes up with it. There's certainly some companies that have far more influence than others in said standards, but
hardware is more likely to be pushed by a company because there's a lot more capital outlay involved in, say, USB or CD. Like it was Philips and Sony that own the trademark to CD-ROM or to compact disc. Sorry.
Mm-hmm. A lot of companies, yeah.
Yeah, you have these giant projects that is like, so those kinds of things. But software is a different animal. It takes me nothing more than an hour to go home and write a library that everybody wants. So there's very little barrier to entry to it, and it doesn't have to be pushed by a large organization, although it frequently is because those are the guys that are down in the trenches. Those engineers are the ones dealing with the issues. They know it like the back of their hand. The good ideas are likely to come out of those kinds of places. So
it's going to be slower than standard software standards, though, only because it does require hardware to be created. So you're on that life cycle, and so people can invent great software standards, but it's going to be 6 months to a year before that great new software standard is put into actual consumer devices.
There's also the case of having a de facto standard, which like x86, say, just like CPU instruction set, x86, and it's kind of a standard by now. I don't know if it was internally in Intel for sure. I don't know if it's ever been some kind of a public open standard, but AMD, this is weird. Intel CPUs license the 64-bit instruction set from AMD. So AMD actually has the standard 64-bit x86 implementation. Intel licenses it from them. They license x86 from Intel. And it's weird because Intel went and tried to push a 64-bit x86 standard that fell flat on its face. IA64, I don't know if anyone remembers that one or not, but a few chips used it. I don't even know if it's even still in use, but still supported in some places. So yeah, hardware's a little bit of a different game, but yeah, what's a standard?
Good deal. Well, we'll stick around for more questions after if you want to talk to any of us, talk amongst yourselves. I also want to thank Yama Valdivia for organizing this on Meetup. Thank you very much, and thank you to Neustar and our panelists for tonight's discussion. There's more food and drinks in the back. Thank you, guys.
Thank you.
Hey, what's your